Hello and welcome back to Let's Code Physics. We are continuing to have some fun with our rope simulator. Last time we got it to interact with some surfaces. There's still a few glitches to work out there, but I think we've got it good enough to where we can proceed with making a simple cut the rope style game. If you have not played Cut the Rope, feel free to pause this, go ahead and get it on your mobile phone or your tablet and play a few rounds. It's a lot of fun. It involves all this rope physics we've been talking about, where you have to treat a rope as a series of springs. Really, in order to make this thing emulate a cut the rope style game, I haven't had to change much. I went over to my FTL code and borrowed this grabbing code that we attach to the mouse down command. So that just means that whenever you click on the screen, it's going to initiate this grab subroutine. And basically what it's doing in this loop is it's checking whether you have clicked on one of the atoms or whether you've clicked on one of the springs. I haven't quite gotten it to work for clicking the springs. It doesn't seem to respond to that, I think because the spring's position is defined as the beginning point, which is where the atom is anyway. But I'm going to keep playing around with that to try to make that a little bit easier to work with. Let's see. So what this does then is if you click on an atom, it turns that atom invisible. So basically when you are cutting the rope, you're severing it at one of the connections. It's making one of the springs invisible, and it's also turning off the connection between the neighboring atoms. So this K-list, this is just the spring stiffness that we had earlier, only now I've had to turn it into a list so that we can keep track of what springs still exist. You can see that down here whenever it creates these springs. It also creates the spring stiffness. All of them have the same default value. And then later on when we're calculating the force caused by the springs, instead of just referencing Ks, it's referencing K-list of that particular pair of atoms. And so whenever this gets turned to 0, then there's no more spring force there. So let's see. I've left in my surfaces from last time. We've still got the rope swinging like this. Let's zoom in a little bit. So when I click on this thing, if I successfully click on one of the atoms, and this is one of the things I need to fix today, is it being able to capture one of the springs. Basically, it cuts the spring connection there. So you can see we've gotten rid of one of the atoms, so it's like we've got a rope here and a separate rope here that's actually managed to bounce down onto the bottom floor there. So what I'd like to do today is a couple things. First, I want to see if I can fix this spring issue where it's not selecting the, where it's not picking up on the spring, and see if we can come up with some way of having you click on the actual physical spring and it cutting it there, because otherwise you're stuck searching for those joining points in between the springs. And then the other thing I'd like to do is this will be more straightforward, is turn the surfaces into a little bucket, and then the object of the game would be to try to get the the bottom of the rope to fall into the bucket. So we'll make the last atom bigger, so that'll be like the candy or something like that. So in looking at this, I'm thinking that one way to do this would be, instead of asking what happens if the instead of asking if you've selected one of the objects, because it only defines the object as, that particular point it's looking like, I wonder if we could define it as looking at the space for the spring. So in other words, let's comment this part out, because we might need it later, if we want to go back to the old version. So what I'm thinking of here is I'm thinking of taking a look at the location of the event. So if event.pause, and here we're going to do a little bit of pseudocode, is in the space of the spring. Right, so I need to get some idea of looking where the spring is extended to, not just the location that it associates with the spring. So what I need to do is I need to get for example, the top of the spring, the bottom of the spring, and then the I suppose the radius of the spring. So you can think of the springs as being a cylinder. So basically, if I click anywhere in that cylinder, I want to be able to find that out. Actually, let me even, before I do that, I've made the assumption that that dot pos is an attribute of this object event. So let's actually see whether that's even a thing. Let's see. Let's put in our our colon here. So then let's have it print event.pos. Actually, let's do this. So when I click somewhere, it's going, if I click within this area, it's going to tell me you clicked on, and then it'll say event.pos. So if I see this and then I get an error for event.pos doesn't exist, and I know that I don't want to do that. It might be this event.picpos. I'm not sure. Let's find out. Okay, so swinging back and forth. Let's zoom in here. Oh, cool. You clicked on this. So event.pos is a thing, in fact. Awesome. Now the trick is, okay, cool. Okay, so does it know that even if I don't click on one of the springs, or on one of the atoms, excuse me. So let's put that outside the loop. So now it'll check for this no matter where I click. So let's give that a try. And let's see here. You clicked on this, you clicked on this, you clicked on this. Okay, cool. And it's always taking it as being at z equals 0, as long as I have that orientation. Yeah, if I change my orientation, it'll change to there. Okay. Oh, look, I was still able to cut the rope. All right. Cool. Okay, so event.pos is actually a thing. So that's good to know. So what I need to do now is start figuring out sort of the space that's taken up by the spring. Let's see here. So what I need is some edges, kind of like what we did with our surfaces down here. I had a left edge, a right edge, bottom edge, top edge, etc. Okay, I think the way I want to do this, let's maybe get a diagram out here. Because as always, I start out thinking this is going to be something simple, and then I get into the geometry, and it's actually quite complicated. So let's see. Where's my whiteboard? There's my whiteboard. Okay, so these springs, you can think of them as a cylinder, right? So they've got a radius that's specified, and they've got a length that's specified, but they've also got this direction, right? So what I want to know is I want to be able to tell whether some given point is inside of that cylinder. Okay, so let's think about this. And actually, I wonder if I only need to... I wonder if I only need to worry about the... because it broke on one of these. I wonder whether I only need to worry about the... No, I think I do need to worry about X, Y, and Z, because this thing could be rotated back and forth. So I'm actually making something that's more challenging than cut the rope, because I'm making a I'm making a three-dimensional version. Maybe I should start with the three-dimensional version. How about that? Let's move on to the three-dimensional version in a little bit. So for right now, let's assume that nobody's going to rotate the screen on us. And in fact, we can rotate the screen and then see if the code still works. So let's think of it this way. So we've got this spring. So we're looking at the cylinder head on. So we're ignoring the z direction. And so I want to know whether a given point is inside this rectangle. Now this rectangle can be rotated kind of any which way. So let's think about this. So the point that we pick, let's call that xp and xs, right? So that'll be xs, no. YP. I don't know why I said XS. Oh, you know what I was thinking? Back to police officer and speeder from the first video that we did together. Y pick, or X pick and Y pick. There we go. So that'll be the location of this thing. And I guess what I'm really concerned about is whether it's within these corners. Okay, so so I would need to think about the four corners of this thing. So call those point 1, point 2, point 3, and point 4. It doesn't really matter how you label them. And so what I want to know is I want to know whether whether this point xp, yp is inside these points x1, y1, x2, y2, x3, y3, and x4, y4. So I guess the way it needs to work is that there needs to be at least one of these that that has a greater y, at least one of these that has a lesser y, at least one of these that has a lesser x, and at least one of these that has a greater x. Okay. Okay, so for example, what I could define would be a top point. So I could define a top that has a top corners. Now, so maybe instead of thinking of edges, I should think of the corners. So the top is going to be the corner with the greatest y, corner with the highest y. The bottom is going to be the corner with the lowest y. And then I could do the same thing with the x and the with the x's. I can make a left that has the lowest x and a right that has the highest x. And then I could just compare those values against this point's value. Okay, cool. So let's do this then. I need to figure out a way to translate these into the spring. So basically the way it works is you get a point over here, and that's the spring's position. And then you get a point over here on the other end that is the spring's position plus its axis. Not post-axis, but position plus axis. There we go. Okay. So if I set it up that way, that would get me sort of the central point here and the central point here, and then I could simply add this distance going in this direction that would be perpendicular to the axis. So this is going to be this distance right here, and I should have drawn this bigger, is going to be half the radius in this distance. So I need to figure out a way to get a vector that's perpendicular to the axis in the xy direction. Okay, so let's do this one. Let's just start calling these things corner 1, corner 2, corner 3, corner 4, etc. So corner 1, actually before I do, yeah. So let's say corner 1 is equal to, we'll start out with the position vector. So we'll start out with the position of the spring. So we'll say spring list of i.pos. And then I want to say plus half of whatever this direction is, plus 0.5 times perp_vec. So perp_vec is going to be this vector here that points perpendicular to the axis. So perp_vec is going to be this vector here that's perpendicular to the axis. The best way that I know to make sure that you get a perpendicular vector is to take a cross product. And the thing we could take the cross product of would be, we could say that perpendicular vector is going to equal the z-axis cross with the spring axis. So if I take right-hand rule, if I do z cross post-axis, yeah, that will point in the direction of the perp vector here. I mean, it doesn't really matter because I'll just do plus one way and then minus the other way, and then we'll figure out the maxes and the mins later. Okay, cool. I like this. So now my question is, does VPython know how to take a cross product? I have not done that yet. I don't think we've had to do that in... Oh, we have had to do that in class. Yes, it does take a cross product. VPython cross product. There we go. Let's see here. Okay, yeah, so you take one vector dot cross the other vector. Okay. I think. Let's actually open the website and find out. So let's see here. Let's take a look at the cross product. Cross A comma B. Okay, cool. there are lots of different things. All right, I will come back and learn more about their vectors later. So, okay, so what we're going to do is we're going to say that the perpendicular vector is equal to perp_vec is equal to the cross product of the z direction. So I need to get a z hat equal to vector 0, 0, 1, which is the sector where Earth is located in Star Trek, by the way. Cross z hat z har. Har z har har. Cross z hat with the spring list of I dot axis. Cool. So I've taken the cross product of z hat with the springs axis, cross product of z hat with the spring axis. Cool. So we'll say, okay, now that gets me a good direction, but that doesn't necessarily get me the magnitude, right? Because this thing, axis, the springs axis also contains the length, and that's not necessarily the length that I want this to be. So let's do this. Let's turn perp_vec into a unit vector, divide by magnitude of perp_vec. So whenever you have a vector, if you divide it by its magnitude, you automatically get a vector of magnitude 1 that's pointing in the direction that you want. It's a neat math thing. If I were writing a math textbook, I would call it a vector pro tip, but they don't let me write math textbooks, so you know that's okay. Times, let's see here, times the, I suppose it would be times the radius of the spring. So spring list of I dot radius. And so that means I actually don't need this half on there because the radius is going from the center to the outside. So we'll say corner 1 equals spring list of I dot pos plus perp_vec. We'll say corner 2. Oops, excuse me, wrong line. Corner 2 is that thing minus perp_vec. So basically, no matter which direction perp_vec gets defined, one of them is going to be going this way, the other is going to be going the other way. Now the trick is I have to get from this point to corner 3 and corner 4. And for that, we have to start at the position plus the axis. So I can take these, say copy, paste, make this corner 3, make this corner 4. And now all I need to do, excuse me, now all I need to do is take this and add to it spring list of I dot axis, because the beginning of the spring is at spring list dot pos, the end of the spring is at spring list dot pos plus spring list dot axis. Again, we are going to write a Let's Code Physics Dr. Seuss book at some point. Cool. So we get a corner 1, corner 2, corner 3, corner 4. Okay. And this is something I will have to update every time I click because the rope is swinging back and forth. Cool. So now what I need to do is I need to turn those into which one is at the top, which one is at the bottom, etc. So let's do this. Let's say that, so I need some new things called top corner, left corner, right corner, etc., etc. So let's define a top corner equal to corner 1, a bottom corner equal to corner 2, a left corner equal to corner 3, and a right corner equal to corner 4. And it, oh, actually, let's start them all at 1, actually. Yeah. All right, here's the deal, right? When you've got a rectangle that's oriented in space, only one corner can be on the top, only one corner can be on the bottom, only one can be on the left, only one can be on the right. The only way you can have it where they share one is if it's at a if one of the sides is, or excuse me, if two of the sides are parallel to the ground, to the y-axis, or the x-axis, excuse me, or to the y-axis, because if two edges are parallel to one, the other two edges are parallel to the other, because it makes right angles. Awesome. So if I go over and loop over the possibilities and evaluate their x's and their y's, I should be able to get them sorted out. So let's do this. Let's see, we are already in... While okay, yeah. So now what I want to do is while I corner equals, okay, I need to make a change to this. Is is less than or equal to, oh, actually, you know what? Somebody was just commenting, you know, you can use a for loop in Python, right? And I've been hesitant to do that. Let's actually learn how to do that now, because I think that'll be helpful in this situation. For loop Python wiki, awesome. Because I've just been sticking with while loops because that's what my student's textbook does. So I've just been in the habit of saying, okay, I'll just use a while loop, and one of these days I'll get to a for loop. Let's see here. For loop from 0 to 2. Okay. And I think I can just use this with a list. Excuse me. For x in range. Yeah, see, this is, they always, okay, so I can make a list. Okay, for x in a list. Okay, perfect. So let's do this. Let's make this corner list equals corner 1, corner 2, corner 3, corner 4. And now we're going to say for corner in corner list. And now I'm literally looping over this. I don't even need a counter anymore. Awesome. Okay, so let's take a look at the top corner first. So if corner dot y is greater than top corner dot y, then you need to make top corner equal to the current corner. Okay, so basically what this is saying is the corner that you're looking at, like let's say for example that you started out with this corner here and then you start looping over the corners. When you get to this corner here, you see that this corner that you're looping over has a higher y value than this one, so you call this one now the top corner instead of this one because they're all just being defaulted to the first one. That example doesn't work because corner 1 is the top one here, but you'll see what I mean in a second. So let's see, if corner.y is greater than the top corner, then the corner that you're currently looking at becomes the top corner. Cool. And then we can do the same thing for the bottom. Just change this top to a bottom and make this a less than. So for example, we start out with bottom corner equals corner 1. So when it gets to 2, it's going to say, okay, the y coordinate of corner 2 is less than that of the current top corner, so let's make this the current top corner. Then it goes to number 3. It says, bottom corner. And it'll say, okay, this corner, the y component, is less than the y component of this corner, so let's make this one the new bottom corner. Then it comes to 4. It says this corner's y component is greater than this one, so we're not going to touch a bottom corner anymore. We're just going to leave it there. I think I used all the right words there. Not going to go back and try it again. Then I can do the same thing with the left and the right. Left and the right. Wonderful album there. Or Royal Crown Review. Oops, forgot bottom corner there. So here, let's see here. Now we're doing the right corner because we're saying if it's greater than this. Yeah, this is the greatest challenge, is just changing everything that needs to be changed. Let's go to left, X, and we're changing this one to left. Okay, so let's double check this. Greater than top, top. Yes, Y, Y. Y, Y, less than bottom, bottom. X, X, greater than right, right. X, X, less than left, left. Okay, so if I've done that correctly, the code should now have identified what are the coordinates of the top corner, the bottom corner, the right corner, and the left corner. Cool. So let's do this. If event.pick equals atomleft, or if event.pause. And now what we need to do is we need to check 4 things. We need to check that event.pause.x is inside this range between the left corner and the right corner. So it needs to be greater than the left but less than the right. So let's say if this is greater than the left corner.x and event.position.x is less than the right corner.x. And now I need to do the same thing with the y's. I need to check to make sure that this is less than the top corner's y position, but greater than the bottom corner's y position. So we're going to say if event.position.y is greater than the top corner.y, and event.position.y is less than the bottom corner position y. This is now like the 3rd time I've done this type of check. It's kind of becoming nice and routine for me. Between this code and the FDL code, I've had to put this in several times. So let's double check this. We've got the y position is less than the bottom's y. Oops, I got those backwards. So let's flip these. So why would proofread? So if its y position is greater than the bottom's y position, if its y position is less than the top's y position, if its x position is less than the right's x position, and if its, come on, x position is greater than the left x position. Okay, cool. So we're saying if, etc., etc. So if you happen to click on an atom, great. Or if this is true, okay, I don't need the pseudocode anymore. Right, okay, I've got all my parentheses taken care of. Then it executes this part. Okay, let's see whether that worked. First, let's try clicking somewhere outside. Okay, we had a little bit of problem there. It's trying to find something outside the range. Let's see here. Click, click. Vector attribute has no position pause. Oops! Right, if this thing is a vector, I don't need to call it position. Oh yeah. I don't need corner dot position. Wait a minute. What is it saying is a problem here? Oh, bottom corner dot pause dot y. Oops. I got pause happy. I just, I try to maintain my positivity, Let's see here. I've got bottom, top, right, left. It also gave me a problem with the index being out of range. I think. Did it? Okay, let's see here. Oh, it's giving me an index list out of range with perpvec. Okay, so why does it not like the perpvec calculation? Cross z hat spring list of I dot axis. Oh, because my spring list is always one less than the atom list. Okay, spring list -1, spring list I -1. I -1, I -1, I -1, I -1. I just -1s all day long, I tell you. Let's double check for any others. Let's see, spring list of I. Nope, okay, we're good to go there. Okay, let's try that again. All right, let's watch for that again. Okay, I'm not getting that error. Woohoo! Oh man, that was so much easier. Oh my goodness. Okay, let's take a look here. Click. I can click anywhere now. Oh, look, I got it down to one atom. I have split the rope down to a single atom, and look. Right. It's not going to check for the top atom. Oh my gosh, that worked on the second try. I'm so proud of that. Wow. Okay. Let's see. Let's clean this up a little bit here. Let's see here. So here we're going to define springs corners in the XY plane. This is to remind myself of what is going on here. Okay. And here we are. Check. Oops. Check whether rope has been cut. There we go. Awesome. Okay, so now I can literally click anywhere that the rope is, and it comes flying off. Oh my goodness, that is so cool. Wow. Okay, I'm gonna do something really quick here. So we've accomplished the first goal. Wow, I thought that was gonna take longer and require some cuts or something, but wow, that's really great. Here's something I'm going to do is that that bottom surface, let's extend that out a bit, because I don't want the thing just kind of like falling off the edge like that, like you saw. I want to still be able to play around with it. So I'm wondering if, gosh, if I make that bigger, the thing is going to zoom out. So let's do this. Instead of it being, oh, I know what I can do. Let's make this thing enormous, and then we'll make it invisible. So let's say this thing is 200 rope lengths by 200 rope lengths. But let's make the visible equal to false. Okay, cool. And now it just leaves me there. So now whenever I click on this thing, click, click. Oh, come on, buddy. We were working just a second ago. There we go. Oh, and there it just lands on there. Let's restart that. Because I want to show that it'll get caught down there at the bottom. Okay, cool. And so, okay, so now it's just falling until it reaches the invisible infinitely big floor. Or basically infinitely big floor. Okay, cool. So we've got it to where we can click anywhere on the rope and it'll cut it. That's pretty cool. Have I set up the center for this view yet? Because it's, I feel like that should be higher. Or no, I feel like that should be lower. So let's go with maybe 2 times in atoms times L0. No. Let's go with maybe 4 times. I don't feel like that is doing what I want it to. Because I should be shifting the center down. No, I think it's automatically changing it. Oh well, it's within view now. Okay, cool. So what I'd like to do now is I would like to take this this surface right here and just turn it into a little bucket. So let's see. Yeah, so I still haven't solved the problem with that thing that was giving, but it's not going to stop me from making a game out of this. Let's see here. So we've got this surface. I want to make another one that is immediately to the left of it. Let's see. So this current one, its position is there. Oh, I know how to get it. Let's see here. Let's have its left position be, and I'm glad I defined these. Let's have its left position be at the left edge of surface list of 1. Now I'm so glad I defined that, because now wherever I put the bottom of the bucket, the other part of the bucket will be there. And then let's say here the Y position will be at the bottom edge of surface list of 1, 0, cool. And so I need to now kind of flip this thing's size. So let's make this into, let's make this its height and 0.2 its width. Cool. So I'm basically taking the previous one and moving it over, flipping it. Let's see if that works. Invalid syntax, of course. What did I do wrong? Oh, I need to close up my parentheses there. I closed up my parentheses there. Cool. Okay, that's not exactly what I'd wanted. Oh, right. I need to shift this thing up by half of its width, or by half of its height. So let's see here. So this is... Oh, actually, I can make this thing even easier, can't I? I can make this one surface list of 1 dot size dot y, because I just flipped them manually, but I could just have the code flip them for me. Let's say paste here, size dot x, and then here, actually, yeah, let's just mimic this one's size dot z. And now the position needs to be the bottom edge of surface list 1 plus half of, I want it to go up by half of its own width. So that's going to be plus half of surface list of 1 dot size dot x, I think will work. Yes, okay, I got a little L there, and it should actually stop the thing from... Ooh, look at that, it knocked into it. Okay, I'm going to need to move this whole thing down, I think. Still, that's pretty cool. Okay, so let's move this whole arrangement down. Let's see here. It's currently at in atoms plus 10. So let's actually make it like 2 times in atoms. 5. Okay, cool. So now this part will swing freely. Awesome. Now I need a right edge, a right edge of the box. And here we go. Copy, paste. So now I want the size to be the same. It's the position that I want to be different. So now, instead of it being at the left edge, I want it to be at the right edge of surface list 1. And there should be something I need to change. Okay, cool. So I've got myself my rope. I've got a little bucket. And now my goal is to try to get the bottom of the rope to fall into the bucket. We have a winner. All right, cool. So I have just made a fun little cut the rope game and I've won it. All right, that makes me feel pretty good. So, actually, this is a perfect opportunity to test whether this still works in the, it does work when I rotate the screen. Oh, that's so amazing. Yeah, I'll need to turn on the drag force or something to get rid of that bounciness. Maybe when it collides, I should send it back with like half the velocity or something like that. Cool. So to finish this out, let's see here. So the last atom, I'm technically already coloring green, and let's make its size, its radius, about 10 times as big as it currently is, times 10. I'll go for 50. Not to 50! Oh, yeah, there we go. So there's Omnom's candy. Whoosh. I haven't changed the mass of that, so it's not like it's swinging differently. And, almost made it. Oh, whoops. And it is, oh, dear. Oops. Omnom's not getting his candy, is he? Let's see. 50 may have been a bit much. Let's see. Okay, yeah, that's a much more reasonable looking candy. It swings this way. I need to cut it at the right moment to get it to fall in. I need to actually click on the thing. There we go. And there we go. Omnom has gotten his candy. Okay, cool. So we've gotten the basic elements down for a very simple cut the rope style game. That is actually kind of fun. Would be really fun now to get the thing spinning in 3 dimensions, and then you have to try to get in there. For that, I would have to add a wall here and a wall at the back. So what I'll do in the next episode is start creating some more complicated scenarios for what we might need to do for a cut the rope style game. So thank you so much for watching. I will see you next time. Bye bye.